Hello, good evening, all of you. I'm Vikas Sir and I welcome you all to yet another knowledgeful lecture on the fluid mechanics subject. So today we'll be studying about the topic of viscous flow through pipe. So very good evening to all my dear students. Welcome to this session on viscous flow through pipe. I hope your preparation for GATE 2021 is going well, and I hope you are enjoying these lectures in the late night series, and I hope you are getting proper information and complete knowledge about these topics. So, very good evening, all of you. Hi, Joel, George. Good evening. Welcome to the session. So, hey, good evening, all of you. Welcome to this session on viscous flow through pipe. Hi, Kalam. Good evening. Welcome to the session. In the last session, we were having a discussion on losses through the pipe, and that session went quite well. Why this late night class, sir? Please arrange in daytime, please. Hi, good evening, Ashwin. Yeah, definitely. Actually, that was the main idea about this late night series was that maybe some of the students who are preparing for GATE exam, they don't have proper time during the day for their preparation. So that is why we are providing you these lectures in the evening, in the late night. Yeah, it is difficult to attend these lectures, especially if you are having some morning. You have to go for a job in the morning. So, but the main idea about this late night series was to help those students who are preparing for some exams, like GATE exam, especially, and they don't have much time in the day for their preparation. So, very good evening, Neeraj Kumar, Hemant Rajan. Very good evening, cold evening, Rajesh Prajapati. Good evening, Shaumitra, Mohan Sundar, Akhilesh Khadse. Very good evening, everyone, and welcome to this session on viscous flow through pipe. I hope you guys had a very great day and good day, and definitely this day will also over with a very amazing session. You are definitely going to learn a lot in this session. Now, talking about the last lecture that you have attended in the losses through the pipe, if you remember, my dear students, that we have completed the theory of losses through the pipe, then suddenly there was a technical issue in my laptop which did not allow my session to continue. So because of that, you guys have also waited for some time in the night. And let me tell you what happened afterwards. When I closed the session, I have to restart my laptop, and then the problem was resolved. Okay, but the problem was if I would have restarted my session yesterday during the session, then maybe there was a chance that the session may also get over. So that is why the problem was regarding the restarting of the. I have to restart the laptop for basically overcoming the problem. Basically, that was some problem with my PPT. My PowerPoint presentation got corrupted because of some reasons. So don't worry, we will be covering that problem today. Today we'll be solving those numericals first of losses through the pipe, and then we'll be come to the topic of viscous flow through pipe. Okay. Hi Vikas Yadav, good evening. Mohit Kundu, good evening. Ratna Sanu has good evening. Hi Hardeep, good evening. So very good evening to everyone, those who have joined me for the session. One more important thing I have to tell you that, as you know, my PDF, my PPT, my laptop was basically completely hanged yesterday, and also I was not able to save my PPT. So that is why I was not able to provide you the PDF of the last lecture. So I'm really sorry about that. I tried a lot yesterday to save the PDFs, but ultimately I have to restart my laptop, and because of that I was not able to save the PPT that I have taught you yesterday. Okay, so really sorry, that is why I was not able to provide you the PDF of the last lecture. Okay, so my dear students, please quickly join me for the session. Everyone, hurry up. Hurry up, everyone, quickly join me for the session. And those who have joined me already, please like the session. Hi, Shushmita Das, good evening. Welcome to the session. Those who have already joined me, please also like the session. Are we completing FM today? No, Susmita, we are not completing the FM. It is not possible to complete a subject like fluid mechanics in one class. Okay, basically these are the series of lectures I'm providing on the YT channel, YouTube channel, in which I'm completing some particular topics. I will not be completing the entire fluid mechanics. So those who have joined me, please like the session, share the session, and also please do subscribe our channel if you have not done yet. Okay, so let's start the session without having more time giving in discussion, because we have much plenty of things to study today. So my dear students, let's start the session now. So let's begin the session. So I would like to start with my introduction. That is a formally introduction about myself. I am Vikas Sir. I have 5+ year teaching experience. I did my MTech in thermal engineering from Thapar University and mentored more than 10,000 plus engineering aspirants for different exams like GATE, engineering, ESE and SSCJ. My area of expertise includes subjects of fluid mechanics, thermal applied and heat transfer subject. So let's begin with what we have completed yesterday. The last topic that we were up in the last lecture was losses through the pipe, but in that we were not able to solve the questions because of some fault in my laptop, because of some problem in my laptop. So we'll be completing those numerical first, and then we'll be starting the theory of today's lecture. So guys, I will be giving you some time for solving these questions. This is question 1 that we have to actually discuss yesterday, but now we are solving it today. Yes, two pipes A and B with detail as below are connected in the parallel between 2 points. We are having a pipe A which is having the diameter length of 150 meter, diameter 10 centimeter and friction factor 0.02. Another pipe which is having the length of 200 meter, diameter of 8 centimeter and friction factor of 0.015. The diameter of an equivalent pipe of length 175 meter and having friction factor of 0.015 is. Kamran is saying it is 12.89. You also studied from Patiala. Okay, are you talking about Thapar University, Hardeep Singh? Because I did my MTech from Thapar University, Patiala. So my dear students, please quickly join me for the session. Please start solving this question. This question actually I gave yesterday in the last class, but unfortunately the class was not able to continue after some time because of some technical issue in my laptop. So we are now completing that portion of questions today. Hurry up, be quick. We have to start the new topic also, viscous flow through pipe. So be quick guys, hurry up. Hurry up, please solve the question. Okay, from Punjabi University. Okay, fine. Yeah, it is just at the in Patiala, yeah, in Patiala, Punjabi University. Come on, be quick, guys. Come on, be quick. Equivalent diameter for a pipe in parallel connection. The pipes in parallel. If you remember, I have told you in the last lecture, there was a formula that I told you. The equivalent diameter power 5 over friction factor into length root was equal to the diameter 1 power 5 F1 L1 plus root of D2 power 5 F2. This formula I told you for the pipe in parallel, for pipe in parallel connection. Didn't you remember this? For pipes in parallel connection, I told you two formula. This formula I told you for pipe in parallel connection with different diameters and length. With different diameters. So you have to use this particular formula. Come on, be quick. The diameter is given of the two pipes. Let us say this is pipe. You can say take a 1 or A, or this is B or 2. You can just put all the values. You will get the value of DE. You have to find this. Very simple formula. Mohit Kundu, you will be getting 12. Okay, you are getting 12.89. Akhilesh is getting 12.11. So why will be neglecting the value of F? Will there be thermodynamics and heat transfer crash course? Ashwin, the crash course of thermodynamics I have already completed. In that I have completed the entire revision of thermodynamics, IC engine, refrigeration, power plant. That is already available in the YouTube channel. You can find that. Okay. But in the late night series also I will be completing the thermodynamics, but not complete thermodynamics, but some important topics. The friction factor are given for both the pipes. Will not be neglecting that. The answer will be 11.66. The answer will be 11.66 centimeter. That will be the answer. If you put all the values, you'll be getting the answer as 11.66 centimeter. Are you getting this value? Anyone? Anyone getting this value? Please tell me. Just put the value. The diameter D1 is equal to what? D1 is equal to 0.1 meter. D2 will be equal to 0.08 meter. L1 is equal to 150 meter. L2 is equal to 200 meter. For here the equivalent length is equal to 175 meter and the equivalent friction factor is also given 0.015. Everything is given. Just put all the values, will be getting the equivalent diameter. Will be getting the equivalent diameter, that is, yeah, you will be getting 0.116 meter, that is 11.6 centimeter. Are you getting this value? Are you getting this value, everyone? You have already studied the theory of mechanics and thermo. Okay, so my dear, if you have already studied the theory part of fluid mechanics and thermo, so you should only do the practice of the questions. You should start solving the previous year questions and attempt the mock test. Okay, that is the best you can do now. Let's move on to the next question, question number 2. Two reservoirs are connected through a 200-meter long 0.4 meter diameter pipe. The head difference between the two reservoirs is 10 meter. The fanning friction factor is given as 0.01. Fanning friction coefficient is 0.01. Including all major and minor losses, the velocity in the pipe is. So how can we solve this problem? We are having two reservoirs. Let us say we are having two reservoirs, and these two reservoirs are connected with a pipe. They are connected with a pipe, let's say like this. Okay, they are connected with a pipes. The two reservoirs are connected with a pipe. The length of the pipe is given here is, the length of the pipe is given as 2000 meter, and the diameter of the pipe is, the diameter of the pipe here is given as 0.4. The diameter is equal to 0.4 meter. The head difference, let us say that this is the level of the water in the pipe, level of the, we can say whatever is the fluid, and this is the level of the fluid here. So basically you can see the difference of the level of the fluid here between both the pipes is equal to 10 meter. Okay. Now what you have to find? You have to find the velocity in the pipe. You have to find the velocity in this pipe. What is the velocity of the fluid in the pipe? Okay. So they have given the total head difference. Difference of head between the two pipes is given. The difference of head between the two pipes is given as how much? That is 10 meter. Okay. So H is equal to 10 meter. Now tell me, if these two pipes are connected, these two reservoirs are connected, how many types of losses will be there? One will be the major loss, which will be FLV square by 2GD. Apart from that, there will be loss due to entry, when the fluid will enter into this, from this tank into this pipe, and one will be loss of exit, when the fluid will entry, fluid will exit from this pipe into the big other tank. Okay, so that will be simply equal to the total head loss. H will be equal to FLV square by 2GD. What is the entry loss? Entry loss is equal to sudden contraction loss, which is 0.5 of V square by 2G. What is exit loss? Exit loss is equal to V square by 2G, simple. So my dear, you have to include the major and minor losses in this situation. They have already given the difference of the head between the two reservoirs, that is 10 meter. You have to simply find the velocity. They have given the fanning friction of coefficient. This is friction factor, so you have to multiply with 4. Again, I told you the formula for head loss, because they have given fanning friction coefficient, which is fanning friction coefficient, not friction factor, so you have to multiply with 4. So this will simply become 10 is equal to 4 into 0.01 into L. What is the length is 2000 into V square by 2 into 9.81 into D. D is 0.4 plus 0.5 of V square by 2 into 9.81 plus V square by 2 into 9.81. If you solve it, you will be getting the value of velocity. What is the velocity you are getting? Please tell me, everyone. What velocity you are getting in this question? You will be getting velocity as 0.986 meter per second. Are you getting the answer, everyone? 0.986 meter per second. Akhilesh is getting 0.986. Yes. Is everybody getting this velocity? Hi Hitesh Arora, very good evening. Welcome to the session. Welcome to this session. We are solving some questions that we were not able to solve in the last lecture of losses through the pipe because of the technical issue. So we are firstly solving those questions. Then we'll be starting the theory of today's session, viscous flow through pipe. How many parts I have made for FM? I have made 7 parts. 3 parts already completed. This is the 4th part. Now only 3 parts are left. Okay. So basically in the late night series, we are not completing the entire subjects. We will be completing only those important topics which have very high weightage in particular subject. Okay. That is the main motive of this series, to make you strong in those topics which are very, very important. So the answer will be 0.986. Are you getting the answer, everyone? Okay. So let's move on to the next question. Very good. Ashwin is getting, Kamran is getting, Akhilesh is getting. Hurry up, guys. Start. Take out your pen calculator. It's not important if you are not having a virtual calculator. You can take a manual one. But take out your calculator and quickly solve the question. Hurry up. Increase the speed. Next question. Question number 3. A horizontal pipe of diameter 400 mm is suddenly contracted to a diameter of 150 mm. The flow rate is 250 liter per second and the head loss due to sudden contraction is 1.8 meter. The coefficient of contraction is, tell me everyone, what is the answer? Be quick. Hurry up, be quick, my dear. Yes, Vikas, that is correct for the last question. See guys, if you will be simply watching the session, not solving the questions, then you are not completely participating in the session. If you really want to learn something, you have to get completely into that thing. Okay, so take out your pen, calculator, a rough paper or a notebook, start solving these questions. Okay, so you have the advantage that you can do all that in your blanket. You don't have to come out in your study room and you don't have to expose yourself to the cold like I'm doing, right? So my dear students, please do participate in the session and hurry up, be quick. The head loss due to sudden contraction is equal to 1 by coefficient of contraction minus 1 whole square into V2 square by 2G. I told you this formula for the loss due to sudden contraction. Didn't I told you this formula? Now in this formula you have to find the coefficient of contraction. This you have to find from the formula. They have given the head loss due to contraction, which is 1.8 meter. This will be 1 by coefficient of contraction minus 1 whole square V2 square. What is the V2 here? V2 you have to find from here. They have given the diameter. The diameter is given as 400 mm, which will be 0.4 meter. It is suddenly contracted to what diameter? It is contracted to 150 mm, which is 0.15 meter. The discharge is given as 250 liter per second. That is, discharge is given as 0.25 meter cube per second. It is very important for you to reduce all the important terms into the standard units or in the SI unit. Because discharge is given in liter per second, you have to convert into meter per second, meter cube per second. Now you know that discharge will be equal to area into velocity. Now because you have to find the velocity, you have to put velocity V2 here. So you can also apply that discharge is equal to A1 V1 is equal to A2 V2. So discharge will be equal to A2 into V2. It is equal to pi by 4 into D2 square into V2. Discharge is given already 0.25. It is pi by 4 into D2 square. D2 is equal to 0.15 square into V2. From here you will get the value of V2. What is the value of V2? Please tell me everyone. See guys, you are not making it fast. Hurry up. 14.147 meter per second. This will be the value of V2. If you just put the value of V2 in this equation, that will be 14.147 square by 2 into 9.81 and solve this particular equation, you will get coefficient of contraction is equal to 0.704. Are you getting this value everyone? Or anyone getting this value out here? Yes, you have to be very much careful about the calculation part. If you will make mistake in the calculation, you may not get the right answer. Okay, so be very much careful about the calculation also. Yeah, velocity V2 will be 14.147 meter per second. That is absolutely correct, Ashwin. And the coefficient of contraction will be 0.704. Is anybody getting this value or not? Please tell me. Hurry up guys, hurry up, come on. As we know that we have to start a new topic as well in the session. Yes, Sunil is getting, yes, he is getting the value. Yes, hurry up guys. And those who have joined me for this session, amazing session on the viscous flow through pipe in the late night series, please also give some time to like the session. Yes, are you getting the answer or not? Tell me, my dear students. Are you getting the answer? Yes. 0.71. No, that will be simply 0.704. Exact value will be getting 0.704. Okay, Kamran. Next question. The loss of head in meter when a pipe of diameter 150 mm suddenly enlarged to a diameter 300 mm is. The rate of flow through the pipe is 300 liter per second. This is liter per second. Okay, liter per second. Here you have to find the loss due to sudden expansion. Yes, everybody is getting 0.704. Very good. Very good. It is very good that you are getting the answer correctly. So the loss due to sudden expansion will be equal to V1 minus, this will be, what is the formula for loss due to sudden expansion? It was V1 minus V2 whole square. It was V1 minus V2 whole square by 2g. That was the formula. You just have to find the velocities. The diameter is given here. The diameter D1 is equal to 0.150 meter. The D2 is equal to 0.30 meter. You have to find the value of the velocity because diameter is not important. The velocity is important. So discharge is already given. Discharge is equal to A1 V1 is equal to A2 V2. Now using this formula you can find the value of V1 and V2. Just put the value, you'll be getting the answer. Hurry up guys, be quick. Please be quick, make it quick because we have to start a new topic also. Yes, hurry up, hurry up. I'm giving you 1.5 minutes or 1 minute for solving this question. Since I have already told you the approach, you will be just getting 1.5, you will be getting 1 minute for solving this problem. Yes, be quick, my dear students, be quick. What I have experienced here that the number of students who were watching the session earlier, now they have reduced suddenly. Why? Because when this series have started, there used to be around 70 students in the class. But now I can see the number of students have reduced to just half. Why? Are you not feeling interested for preparation for GATE exam? Or some of the students don't find this timing suitable for the class? Hurry up guys, hurry up, be quick. Neeraj Kumar has got 8.25 as the answer. Be quick guys, hurry up. We need to really increase our speed. Okay, this is how not we have to solve the question. Discharge is given 0.3 meter cube per second. It is equal to pi by 4 into d1 square into v1. From here you will be getting v1. d1 is given. Velocity v1 will be getting as 16.97 meter per second. Similarly, you can get 0.3 is equal to pi by 4 of d2 square into v2. From here, you will be getting v2 is equal to 4.24 meter per second. Just put both values here, you will be getting the answer. That will be, the answer will be 8.254. Okay, that will be 8.254 meter. The answer will be option B. Are you getting 8.254? Yes. Okay, the timings. Well, timings were same. I think timings have not changed because the session started. This session we have when started, the timings were still when the sessions were being taken by Vikas Sir. Then also the timings were same. They were 11 p.m. Right? The timings have not changed. I think from the last 10 days, the class have been going on. Last 20 to 15 days, class have been going on. The timings are same. But what has happened suddenly when I'm taking the subject of fluid mechanics? Are you thinking that this subject is not important? Or do you think that I'm not taking this subject well? What is your input? Please give me your input for this. See, whatever important topics have been mentioned in the GATE syllabus, all those important topics I'm taking in these sessions. Still, I can see the number of candidates, number of students are reduced comparatively as compared to the previous sessions. Hurry up guys, 3 pipes of length 800 meter, 600 meter and 300 meter and of diameter of these 400, 300 are respectively connected in series. The end of the compound pipe is connected to two tanks whose water surface are maintained at a difference of 15 meter. The rate of flow in liter per second of water through the pipe is, you have to find the rate of flow discharge. Yes, hurry up guys, hurry up, be quick. Well, thanks a lot Ashwin for this feedback. I hope you guys are enjoying my sessions, and in the crash course I have completed the revision of FM and thermal, and we have also solved a lot of questions, but this is a particular series. The main idea of this series is to explain you the detail of the theory. Okay, hurry up guys, hurry up, be quick. 3 pipes of length 800 meter, 600 meter and 300 meter. So we are having this, the length of the pipe is given as 800 meter, 600 meter and length 3 is 300 meter. This is the length of the pipe given. Okay, the diameter of the pipe is also given 400 mm, which is 0.4 meter. D2 is equal to 0.3 meter and D3 is equal to 0.2 meter. So my dear students, what you have to do here in this case is we are having two reservoirs. Okay, again we are having two reservoirs. Now these reservoirs are connected in such a way that we are having two pipe connections. We are having two pipe connections. Let us say this is one pipe. Then let us say we are having another pipe here. Let's say The diameter is reduced 400 and 0.3. Let us say diameter is reduced 0.3. Again, it is we are having the diameter reduced. Again, this is say let us say this is like this. This is how the pipes are. Now these pipes are connected to another reservoir like this. Now in this reservoir, if you see the level of the difference of the level of the fluid is given here. What is the difference given here? That difference is given here as 15 meter. Now this same type of question we have already taken into consideration, but the main thing here is if they have not mentioned about the minor losses, will not be taking the minor losses. Because it is a case of pipe in series, the head losses will be added up. The head loss will get added up. Total head loss will be added up. Okay. Now what will be the head loss? It will be equal to FLV square over 2GD. This will be the head loss of all the pipes taken together. This will be equal to FL1 V1 square by 2GD1 plus FL2 V2 square by 2GD2 plus FL3 V3 square by 2GD3. Hurry up, tell me the answer. Neeraj Kumar has got 2681.0257. Let me just check. Okay. So you have got 2681.0257. Let me just check my answer. What is the right answer for this question? You have to find the discharge in this question, which will be 84.79 liter per second. The answer for the discharge will be 84.79 liter per second. This will be the value of discharge. Now for solving this question, I have to tell you that it will be good if you convert this equation in terms of discharge. Now we know that discharge is equal to area into velocity. That is pi by 4 d square into v. It will be good if you can calculate this value of velocity in terms of discharge. If you put that value, what you will be getting here? Then we will be getting here is, as you know that head loss is equal to FLV square by 2GD. So we can also say that this is equal to FL. V is equal to what? This is equal to, V will be equal to 4 into Q by pi d square. This will be equal to 16 into Q square divided by 2 into pi square d power 5 into G. Correct? Now, also in this question, they have given the friction coefficient. They have given friction coefficient as 0.05. They have not given the friction factor. So that means they have given the friction coefficient to also multiply by 4f dash. That will be into 4 also. So if you solve it, you will be getting this value as 2 into 2. This will get cancelled. This will be 32 f dash L q square over pi square G d power 5. This will be again the formula for the head loss. Okay. So if you just put the formula directly, it will be head loss will be equal to HL1 plus HL2 plus HL3. The head loss will get added up. So it is simply equal to, what is the head loss here? That was 32 into f dash L q square divided by pi square G d power 5. This side also it will be equal to 32 into f dash q square divided by pi square into G. In the bracket you will be getting L1 by d1 power 5 plus L2 by d2 over 5 plus L3 by d3 over 5. Now this we can get easily cancelled. So we can simply say that q square d power 5 will be equivalent to L1 d1 power 5, sorry, q square also, q square of, one second, sorry, this is already given in the question. This value is already given. I will not be cancelling it. $84.4, are you getting this value? It will be 32 into f q square, f dash q square divided by pi square g. Okay, this value is given as already 15. Alright, if you put all the values, friction factor is given, L1 is given, L2 given, L3 given, D1, D2, D3 is given, everything is given, you will get the value of discharge as, you will get discharge as 0.0847 meter cube per second, or you will be getting it as 84.4 liter per second. Are you getting this value, everyone? Everyone getting this value? So see, I could have directly applied the Dupit's equation, but in that situation we will not be getting the discharge. Dupit's equation is in terms of length and diameter. Here we have to find that in terms of discharge. So we have basically converted our equation in terms of discharge. Is it clear to everyone? Yes. Is it clear? That was the last question. Now let us quickly hurry up for the, yeah, you will be getting 84.7, 84.78, 0.0847. Okay. So now let us come to the topic of viscous flow through pipe. I would be I will not go very quick, but I will be making you understand the concept of viscous flow very comfortably. See, what is the meaning of viscous flow first of all? As it is quite evident that viscous is related to the concept of viscosity, something related to viscosity, or it is something related to viscous force. Okay, so for the meaning of the viscous flow, no, why we are not considering the minor losses? If they are not mentioned in the question, will not be considering the minor losses. Until and unless they are not mentioned to be considered, we will not be considering the minor losses. In the last question that we have solved earlier, they have already mentioned to include the minor and major losses. That is why we have included the major and minor losses. In this question, they have not asked anything to include the minor losses. If they will not ask anything, you will not be including the minor losses. Okay. Oh, thank you so much, Neeta. Thank you so much. I hope you guys are enjoying the session. And let's basically move forward for viscous flow through pipe, which is the current topic of this session. Okay. So these were few previous year questions from the last topic that we were not able to cover. Okay. So let's basically start the discussion. Vishesh, I'm really sorry if you are having doubt of the last class. Then it is fine. Otherwise, I have to start the topic because already we are running very late. Okay. See, the timings of the classes will not be changed, Ashwin, my dear. So I'm really sorry. Okay. Why can't we use FLV square by 12 d power 5? That is actually FLQ square by 12 d power 5. Okay. See, that formula can also be used, but ultimately, see, you can check that if you will be using that formula, then also you'll be getting the answer. Okay. So my dear, if it is not a problem, you can please give me some time so that I can start this topic. Okay, because this topic is also very, very important. Let me just start this topic of viscous flow through pipe. After that, if you are having any pending doubts or any doubt from this topic, you can ask me. Okay, so let me please start the session. Tomorrow at what time? The timings are same, my dear. Tomorrow timing will also be same, 11 p.m. So now please, if you can excuse me, and if you can please stop bothering in disliking the session. Okay, instead of giving your time in disliking the session, some of the students are doing that also. I don't understand why people think that this session are something to dislike. You are getting some knowledge. If knowledge you are getting, that too on YT channel, you don't have to pay anything for the knowledge, then there is nothing to dislike, my dear. Okay, at least you should appreciate the efforts of the people who are, or of the person who is giving you these classes, especially during this time of okay. So my dear students, let's begin the session. Now please excuse me, I will not be able to see your comments for a while. I'm going to teach you now, so please excuse me, I won't be able to see any comments. Okay, viscosity or viscous force, what is the meaning of this force? Okay, my dear students, so let's start the session. So my dear, what do you understand viscous force? Basically, to be very particular, viscous force, you must have studied that Newton's law of viscosity, tau is equal to mu du by dy. Okay, so in that Newton law of viscosity, you must have studied about the shear stress, right? So what is the meaning of the viscous force? Viscous force is or viscous flow. It is defined as the flow in which the high viscous forces are dominant. Okay, the flow in which viscous forces, viscous effect or viscous effects are dominant. Okay, are called viscous flow. Is called viscous flow. To be, or you can also call it as laminar flow. You can call it as viscous flow or laminar flow. You can call it as viscous flow or laminar flow, to be very precise. Why it is called laminar flow? Because laminar flow is basically defined as, it is you can define a flow to be laminar or turbulent based on a number which is called Reynolds number. Reynolds number tells you that it is equal to ratio of inertia force by viscous force. It is ratio of inertia force by viscous force. What is the inertia force? Inertia force is basically defined as the force which is exactly in opposite to direction of the motion. Okay, and that force, like F is equal to mass into acceleration, in just opposite to this direction of the force applied in a particular direction. The force which opposes the direction of motion, or the force which acts in opposite direction to the force applied, that is called inertia force. That you must have understood from Newton's law of first motion, Newton's first law of motion. Okay, so my dear, what is the meaning of laminar flow? Why it is called viscous flow? The simple meaning is that in the case of laminar flow in the pipe, the Reynolds number is less than equal to 2000. So the simple meaning is that why the laminar flow, why the Reynolds number is less than equal to 2000, because viscous force is more dominant than inertial force. In the laminar force, the viscous force is more dominant than inertial force. That means a laminar flow is defined as highly viscous flow, highly viscous and low velocity. A flow which is characterized by high viscosity and low velocity is called as laminar flow or viscous flow. Okay, so we will be considering the viscous flow through the pipe. We will be discussing about the viscous flow through the pipe, through the pipe. Okay, so my dear, if you try to visualize this laminar flow with the help of this water coming out from this tube, you can see how pleasant it is to visualize the laminar flow. The flow perfectly looks like flowing in a perfect pattern. If you clearly see this, how the pattern is shown here. This is how the pattern of the laminar fluid flow is. You can see that the fluid is exactly following a perfect pattern in this. This is how the laminar flow will take place. You can see that. Is it? You can see this animation also going in the bottom. This is how the laminar fluid flow takes place in perfect streamline, in perfect order. That is called a laminar flow. Why it is taking place in such a perfect manner? Because of high viscous forces. Because of the high viscous forces acting between the fluid particles are able to move like this. In comparison to the laminar flow in the turbulent flow, what you will find, the turbulent flow in comparison to laminar flow has high velocity. It is characterized by high velocity flow and having low viscosity. A flow which has got high velocity and low viscosity, that is called termed as turbulent flow. So in the turbulent flow, the Reynolds number will be greater than equal to 4000. In the case of a pipe flow, if the Reynolds number is greater than equal to 4000, that will be called as turbulent flow. Okay, so that is the major difference between laminar and turbulent flow. Now, I would like to point out your attention about a very important thing. Because we are studying the laminar flow in a pipe, because our topic is laminar flow in a pipe, I would like to point out a very important thing about a topic which is called fully developed flow. What is the meaning of fully developed flow? Is when the flow will take place inside a pipe, then there is a pattern which is followed actually. At the entrance of the pipe, what will happen? The velocity profile will start to grow. Okay, so initially when the fluid will try to enter in the pipe, what will happen? There will be little bit velocity gradients. This kind of velocity gradient will be there. At the surface of the pipe, the fluid particles will be having zero velocity due to no slip condition. Due to no slip condition, the velocity will be zero. But as the flow will proceed inside the pipe, what will happen? There will be some velocity gradient like this. There will be some velocity gradient like this. You can see that. If you join the point of maximum velocity, you will be getting this kind of layer which is called boundary layer. This is a boundary layer which is taking place. Okay, so what is this layer which is formed in the pipe? This is called as boundary layer. This is the layer which is having the maximum velocity. The point at, if you connect the point of maximum velocity, that is free stream velocity, okay, you will be getting this layer which is called boundary layer. Okay, now the important point is what is the meaning of fully developed flow. Fully developed flow is defined as, the condition in a pipe flow, especially in a pipe flow, because in the case of a flow over a plate, the flow is called as fully developing flow. It is never a developed flow. It is always a developing flow. It is only possible for the flow to be fully developed in the case of a flow through pipe. So it is defined as condition in a pipe when velocity profile becomes constant. If velocity profile becomes constant, that condition is called as the fully developed flow, when there is no variation of the velocity profile. So initially, if you notice here, when the flow start to proceed in the pipe, this is how the velocity profile will be. This is how the velocity profile is perfectly flat. It will look like it is perfectly flat like this. But as you further move, the velocity profile will change like this. This is how the velocity profile will change. Okay. Now there will come a point in the fluid flow when the velocity profile will become constant. It will not be changing after some point. As you can see in this region, after this particular point, the velocity profile has become constant. It is not changing. It has become perfectly constant like this. Velocity profile has become perfectly constant in this region. So this region in which the velocity profile has become constant, that is called as fully developed region, in which the velocity profile has become perfectly constant, that is called fully developed region. So this region, my dear, will be called as fully developed region, because after this region, after this particular point, the velocity profile will always be like this. It will be like this. It will be like this. No matter you go in any in this direction, the fluid flow, the velocity profile will be constant like this. Okay, so this condition is called fully developed flow when the velocity profile become constant. Or you can say du by dx in this direction will become constant. This is the meaning of the fully developed flow. Hi Pratik Sonamne, very good evening. Okay, now if you ask this question, after how much distance in the flow through pipe this fully developed condition will be obtained? After how much condition? So for laminar flow, the length after which the length of fluid flow travel after which fully developed flow will be obtained. Fully developed flow will be obtained is called hydrodynamic entrance region. It is also called hydrodynamic entrance length after which fully developed flow will be obtained. So if you see this length will be equal to LE, and this length will be equal to LE by D is equal to 0.07 of Reynolds number. If you have to find the equivalent length, if you have to find the entrance length after which the velocity profile will become constant, that entrance length LE is the entrance length. It is the entrance length in the pipe after which the velocity profile will become constant. There will be no variation of the velocity profile after this particular length in the laminar flow. D is the diameter of the pipe, which is obviously a constant here. Diameter is not varying. Reynolds number, R is the Reynolds number into 0.07. By using this formula, you can find the amount of entrance length after which the velocity profile will become constant in the laminar flow. Clear everyone? Is it clear everyone? So this is something which sometimes is asked in the exams, sometimes very repeatedly not asked, but they will say fully developed laminar flow in a pipe. What is the meaning of this thing? Fully developed flow means in a pipe flow, the region in which the velocity profile is not at all variable, the velocity profile, the variation of the velocity profile becomes constant. There is no variation of velocity profile. That region is called fully developed region or fully developed flow. Okay. Now there is a very important point. In the pipe flow, there are some derivations that I have to tell you. Let us say we are having a pipe flow in a pipe. The fluid is flowing in the pipe. Okay, and we have to find the shear stress distribution for laminar flow through pipe. Okay, so we'll be considering a fluid element. This is a fluid element. Okay, and on this fluid element, we will figure out what kind of forces are acting. So basically, there will be two forces will be acting. One is pressure force, and other is gravity force. Pressure force and gravity force. If you apply the force balance equation, net force is equal to 0. Why? Because there is no acceleration. Because velocity profile is constant, so acceleration will be 0. There will be no acceleration. We can say that there is no acceleration. So my dear, because velocity profile is constant, the velocity variation is not taking place. Du by dx is 0 in fully developed flow. In fully developed flow, the velocity profile becomes constant. So in that situation, there will be no acceleration. So net force will be 0. What will be the net force here? Net force will be equal to pressure force, which is P into the pressure on this particular area is P. On the opposite side, it will be equal to P plus dP by dx. So it will be P into pi r square. Let us say this particular small element is having a very small radius, which is equal to r. A small radius is equal to r for this particular element. Okay, can you make a video on the limits? Wishes, my dear, see, try to understand what I am teaching you. Okay, I can put a video also here, but I hope you have understood about this. You can find a lot of videos on the internet if it is possible, but I hope you have understood the concept, because concept is more important. Okay, just by simply seeing the video you cannot understand the concept. If you understand the concept, you don't need to see any video. So this is the pressure acting on this side of the fluid element. Let us say pressure force is equal to P into pi r square. From the opposite side there will be a pressure which will be P plus del P by del X into dx, which is dx or delta x, we can say delta x into pi r square. And also in opposition to this pressure force there will be a viscous force which will be tau into 2 pi r into delta x. This will in the opposition to the viscous force tau into 2 pi r into delta x equal to 0. See, I am not able to understand why some students come on this channel to make this to what I can say about them. God bless these students who are actually sometimes they want to study and sometimes they create this nonsense in the chat box. Okay, see, if you guys do like that, then my dear students, I will stop reading the comments. It is my humble request, stop doing that. Okay. If you solve it, you will, if you open it, you will be getting P pi r square minus P into pi r square minus del P by del X. One thing I want to tell you, these students who think that they can do anything, they can abuse us, they can come to the session, they can write anything. See, if you understand if you think that we are some young students who are teaching out here, we are some young people like that. See, obviously we are having some experience, that is why we are on this platform teaching you all. One more important thing I have to tell you. This basically shows your upbringings also, the way you treat your faculty or teachers. It shows how you must be treating everyone around you. Okay. So I don't want your respect, but try to behave in the comment box. That is very much important. Okay, because ultimately you have to be an engineer in some company, in some public sectors and something like that. If you don't know how to behave on social media platform, then definitely God bless you all. This will get cancelled out. If you just solve it, you'll be getting this will also get cancelled out. This can basically tau is equal to minus del P by del X into R by 2. You'll be getting this relation for the shear stress. The shear stress will be coming out to be minus of del P by del X of R by 2. Clear everyone? This will be the value of the shear stress we'll be getting here, minus of del P by del X of R by 2. Clear? Now shear stress distribution you have got. This is the shear stress distribution. Tau is equal to minus of del P by del X R by 2. This is R, where R is the local radius. R is defined as a very local, a small radius which is basically varying in the pipe. For local radius means for a very small fluid element. For the small fluid element, the radius which is basically variable, that is called local radius. Okay. So this is the shear stress which will be getting. And what is the condition of how the shear stress will vary in the pipe? When R will become 0, when local radius will become 0, shear stress will become 0. When this R will become R, when this local radius will become equal to the radius of the pipe, in that situation, the tau will become maximum. The shear stress will become maximum. And that maximum shear stress will be equal to this. Clear everyone? Is it clear to everyone? This will be the value of the maximum shear stress you will be getting. So my dear, how the shear stress varies in the pipe? In the pipe flow, the shear stress will be equal to 0 at the center. At center it will be 0 and it will be maximum on the wall. At the wall it will be maximum. So this is, we can say there is a linear variation of the shear stress in the pipe. The variation of shear stress in the pipe is a linear variation. Clear everyone? The variation of shear stress in the pipe is actually a linear variation. Okay. So let us talk about the velocity distribution in the laminar flow through the pipe. To understand the velocity distribution of the laminar flow in the pipe, I would like to say that, let us say we are having a local radius r, and y is the distance from the pipe wall. What is the y here? Y is the distance from pipe wall. Distance from pipe wall. Y is the distance from the pipe wall, r is the local radius. Okay, in which we try to visualize the phenomena of velocity distribution. So we can say that if this is r, this is y, so this total distance will be equal to what? Radius of the pipe. So radius of the pipe will be equal to what? R plus y. Clear? If you differentiate this, you can say dr plus dy will be 0. Why? Because this radius of the pipe is constant. R is radius of pipe. It is a constant thing. Radius of pipe will be constant. This is variable, but this is not a variable. Radius is constant. So this will give you dr will be minus dy. Clear everyone? Is it clear? So my dear students, as you know, the Newton's law of viscosity tau is equal to mu du by dy. If you put the value of Newton's law of viscosity is equal to tau is equal to mu du by dy. If you put y as dy as dr, it will be minus of mu times of du by dr. Okay, clear everyone? Now you also seen that the shear stress you have got, it is equal to minus of del p by del x r by 2. We have just find the shear stress distribution. If you put the value of tau in this relation, you will be getting this equation. This will get cancelled out. Okay. If you further solve it, you will be getting u as equal to, the velocity will be equal to local velocity. This u is the local velocity. Local velocity in the pipe flow is equal to 1 by 4 mu del p by del x r square plus c constant. You will be getting this equation. Okay. So you will be getting du is, if you integrate this, if you integrate it both sides, this will be equal to u is equal to 1 by 2 mu del p by del x r square by 2. So r by square by 2 will give you 1 by 4 mu. Now there will be boundary condition. What boundary condition will be used? There will be two boundary conditions will be used to find this constant. The first boundary condition that we'll be using here is at y is equal to 0, u will be equal to 0. That means at this particular condition, when y will be 0, what will be happening? It will be u will 0. That is the no slip condition also. That is also the no slip condition. And another boundary condition is, another simple boundary condition is local velocity. The local velocity is that velocity which varies with local radius. The velocity which varies with a local radius is called as local velocity. Okay. So my dear students, this is one. Now this is one boundary condition. Other boundary condition is when y will become equal to r. In that situation, what will happen to the velocity? When y will become equal to r, u will become equal to, when r will become 0, r will become equal to r, when this local radius will become equal to radius of the pipe, then u will become equal to 0. Okay. When r will become equal to r, u will become 0. So if you put the value of r as r, you will be getting u will be 0. That will be 1 by 4 mu del p by del x r square plus constant. If we put r is equal to r, this will be r. So you will be getting cs minus 1 by 4 mu del p by del x r square. Now if you put the value of c in this equation, what will be getting here? If you put the value of c in this equation, you will be getting this value. You will be getting u as equal to minus 1 by 4 mu del p by del x r square into 1 minus So I would like to again write it here. Your u was equal to local velocity was equal to 1 by 4 mu del p by del x r square plus constant. Your constant is equal to this. If you put the value of constant, you will be getting 1 by 4 mu del p by del x r square minus 1 by 4 mu del p by del x r square, capital R square, radius of the pipe. If you basically take common 1 by 4 mu, you will be getting this. If you take this as common, minus 1 by 4 mu common del p by del x. If you take this quantity common, and also if you take this quantity common, minus 1 by 4 mu, so this will make the value as r square minus r square. If you take r square common, this will be getting minus 1 by 4 mu del p by del x r square 1 minus r square by r square. So this will be the formula for local velocity. This is the formula for local velocity. Okay. Okay, all the best, Prateek, for your interview at JRF interview at DRDO. But my dear, please focus on in the session also. This relation you get for the local velocity. This is the local velocity you will be getting. So local velocity is equal to minus 1 by 4 mu del p by del x r square. R is the radius of the pipe into 1 minus local velocity square divided by r square. This is the formula you will be getting here. Okay. Now, very important thing I have to tell you here is you have got the value of local velocity as minus 1 by 4 mu del p by del x of r square 1 minus r square by r square. In this relation, this quantity is called as maximum velocity. This is the maximum velocity u. One more important thing I have to point out here, how the velocity distribution takes place in the laminar flow in the pipe. The velocity distribution is a parabolic velocity distribution. This is how the velocity distribution will be. So velocity will be 0 here. It will be maximum at the center. At the center, the velocity will be maximum. Okay. So when r will become 0, if the value of r becomes 0, if r will become 0, u will become maximum. In that condition, the maximum velocity is in the pipe flow. For laminar flow in the pipe, the maximum velocity will be equal to this. Okay. So maximum velocity in the pipe flow will be equal to what? It will be minus 1 by 4 mu del p by del x of r square, where r is the radius of the pipe. Del p by del x is the pressure gradient. It is also called pressure gradient. Okay. Mu is the viscosity. This is the formula for maximum velocity. So maximum velocity takes place at what? At the center of the pipe. This is also called maximum velocity. It is also called as center line velocity. It is also called center line velocity. Because this maximum velocity you get at the center of the pipe. Okay, clear everyone? Maximum velocity, or you can also call it as center line velocity. No problem, my dear. See, two things I have noticed very carefully, that congratulations first of all. Prateek, you are having your interview tomorrow. Another thing I have noticed is that how much your attention level is in the class. You are preparing for some exam which is a very important gate exam, and your attention is that you guys, most of the guys are basically giving their time in the comment in the chat box. So guys, if you will not focus in the lecture, then how you are going to understand it? Yes, please tell me. Say there is enough time for discussion, everything about other things, because right now you have to focus on the lecture, my dear. Okay. Okay. So this is the formula for the This is the formula for the local velocity, and the maximum velocity is equal to this. This is the maximum velocity in this relation. But if you understand that for solving the problems, you need the value of average velocity. Average velocity is required. Why average velocity is required? Because it is very clear that there is a velocity distribution in the pipe. In the pipe flow, velocity is not constant, it is variable. So they will be having zero velocity at the wall, maximum velocity at center, and at that point the velocity will be variable. If you have to find the Reynolds number, which is rho Vd by mu, then how can you find this? How can you find the value of Reynolds number? Because for Reynolds number, we have to put the velocity which has to be average velocity, my dear. Average velocity. Is it right? For finding a Reynolds number, you have to find average velocity. But velocity is varying in the pipe. There is a variation of velocity in the pipe. Right? It is maximum at the center, it is zero at the wall, and it is having a different value at the other portion in the pipe. And for finding the Reynolds number, you have to find the average velocity. You have to find the average velocity. So how can you find the average velocity in the flow through pipe? For that, we have to do some derivation. You know that discharge is equal to area into average velocity. Okay, so we can simply say that your discharge will be equal to, let us say a very small element, a small discharge in the pipe will be equal to local velocity into a local area, small area. After finding this small discharge, we can integrate it to find the total discharge. So this small discharge will be equal to local velocity is equal to what? Local velocity is this. You can put the value of local velocity in this relation. Area will be equal to what? dA will be equal to 2 pi r into dr. This will be the value of area, change in area. If you put the value, you can take this value as constant. This is maximum velocity, this quantity. You can take 2 pi outside, you will be integrating, you will be getting this value for discharge. After integrating, you will be getting, if you integrate this, you will be getting this value for discharge. For the laminar flow through pipe, it is equal to minus pi by 8 mu del p by del x r power 4. Are you able to understand this or not? This is the value of the discharge in the laminar flow through pipe or viscous flow through pipe. If you are not able to understand the integration, I can tell you again. Although it is mentioned everything, this value is equal to what? Maximum velocity, this quantity. Okay. If you just multiply this quantity 2 pi r, if you multiply 2 pi r inside, this will be r minus r cube by r square. If you integrate this, you will be getting r square by 2 minus r power 4 by 4 r square. If you put the limit, you will be getting this quantity. Again, we will be putting maximum velocity as minus 1 by 4 mu del p by del x of r square. If you put the value, you will be getting this value of the discharge. Are you getting this thing? So this is a formula for total discharge. This is a formula for total discharge in the pipe, laminar flow through pipe in terms of radius. If you have to find terms of diameter, you know that r is equal to d by 2. If you put r is equal to d by 2, you will be getting the total discharge in terms of diameter, which will be this. This will be the formula for total discharge in terms of diameter of the pipe. Clear? Clear everyone? See, my dear Ashis, to everyone, please let me cover what I have to teach you in this particular topic. Okay, that is very, very important. Okay. Then after that, if you are having any comments, you can ask me. So you'll be getting this value as total discharge for the laminar flow through pipe, and all this you can also say that it is in terms of radius, it is equal to minus pi by 8 mu del p by del x r power 4. This is the formula for total discharge in terms of radius, and this is in terms of diameter. Okay. Now, why we are finding this total discharge in the laminar flow through pipe? The reason why we are finding the total discharge was we have to find the average velocity. And how you can find the average velocity? The average velocity will be equal to, the total discharge is equal to area into average velocity. What is the area of the pipe? Area will be equal to pi r square. So you can put this value, you can say total discharge is equal to average velocity into area is pi r square. This will get cancelled out. This will be r square. If you solve it, you will be getting this as average velocity. So this is the value of the average velocity of the laminar flow through pipe. In the maximum velocity was equal to what? This is the maximum velocity. This is the maximum velocity, this is the average velocity. If you see the relation between the average and maximum velocity, you will find that the average velocity is equal to half of the maximum velocity for the laminar flow through pipe. This is a relation between the average and maximum velocity. Clear everyone? So I have told you with the help of a derivation here. Clear? Is it clear to everyone? So now I would like to ask you something very personally, that if you guys are thinking that you are not having any question, if you are having any question, you can tell me if the thing is clear to you. Okay, if you are having any problems so far, you can just tell me, let me know. One more thing I am not able to process, that why you guys have so much problem with me, especially some of the students, because this I have noticed only in my session, that some students basically come to the session and this is only my session which get maximum dislikes also. I'm not able to understand that. What is the reason behind that? Is it because I basically also tells you that how you have to behave in the class, some of the students? See, what I offer you, not just lecture, I also give you something which is important morally also as a student, because you are preparing for some exam which will make you which will give you a very important position in some government companies, or you can get selected in some IITs for your masters. So that is why I give you some moral teachings also sometimes. Okay, I don't think it is any problem in that. Okay, so let us understand another part, which is pressure drop in laminar flow through pipe. Okay, if you have to find the pressure drop in laminar flow through pipe, how you can find that? Let us say we are having a flow through a pipe, and in this pipe section, if you have to find what is the variation of pressure in this between these two particular portion in the pipe. Let us say the distance between these two portion is L, and you have to find the pressure drop between two section of the pipe. Let us say this is section 1, this is section 2. So what is the pressure drop between these two particular points in the pipe? How can you find that? Okay, so we know that the average velocity is equal to the half of the maximum velocity. We have just figured it out, right? Average velocity in the pipe is half of maximum velocity, or we can say maximum velocity is equal to 2 times of average velocity. What is maximum velocity? It is equal to minus 1 by 4 mu del p by del x of r square. If you put all the terms on the other side, it will be equal to minus of del p is equal to 8 mu v del x by r square. If you integrate it from 1 to 2, this will be integrated from 0 to L. Let us say the length here is 0 and here it is L. If we have started from 0, this will be L total. The dx will be integrated from 0 to L. So here the limit will be from 1 to 2 and here the limit will be from 0 to L, because length will be varying from 0 to L, right? So if you integrate it, you will be getting P1 minus P2 will be 8 mu L VL by R square. Okay. So my dear students, ultimately what you are going to get? Ultimately, my dear students, you know that this is a pressure drop in terms of radius. But you know that radius is equal to diameter to the power half. Okay. So if you put this value, you will be getting pressure drop in the laminar flow through pipe. This is a formula for pressure drop for laminar flow through pipe. Okay, clear everyone? This is a formula you'll be getting for pressure drop for laminar flow through pipe, and this formula is very, very important. It is equal to 32 into mu VL by d square. Now I have to tell you very important thing. Let us say we are having a pipe, and in that pipe we have to, let us say this is section 1, this is section 2. So between these two sections, the flow through a pipe, if you apply the continuity equation, it will be A1 V1 is equal to A2 V2. Now because this pipe is having constant diameter, the diameter is constant, it is not variable. So A1 will be equal to A2 in this situation, and because A1 is equal to A2, V1 will also be V2. Now if you apply the Bernoulli equation for horizontal pipe, for a real fluid, it will be this. This is the Bernoulli equation for a horizontal pipe for a real fluid. Now because the velocity will be same, it will get cancelled out. And because it is a horizontal pipe, Z1 will be equal to Z2. So ultimately will be getting as the head loss for the laminar flow through horizontal pipe having uniform diameter will be equal to P1 minus P2 by rho g. So we are coming to a very important equation. Very good, Prateek. We are coming to a very important equation. As I have just told you that for laminar flow, P1 minus P2, that is pressure drop, is equal to 32 mu VL by d square. This is the formula for the pressure drop for laminar flow through pipe. If you just put the value of this pressure drop here, you will be getting the head loss will be equal to 32 mu VL by rho into g d square. This is the formula for the head loss you'll be getting for laminar flow through pipe. Clear everyone? And to be very precise, this is the formula you'll be getting for fully developed laminar flow through pipe. Clear? Okay. This is the formula for head loss for fully developed laminar flow through pipe. Okay. So my dear students, we have got the head loss formula. The head loss due to friction for fully developed laminar flow for fully developed pipe is equal to mu 32 into mu VL by rho g d square. But we also cannot ignore this thing that yes, in the last lecture I have told you the formula for head loss due to friction, the major head loss due to friction, which was FLV square by 2 GD. This is also the formula I taught you in the last class. Now if you equate both this formula, this is also the formula for major head loss due to friction, but this formula can be applied anywhere, whether it is laminar flow or turbulent flow, anywhere. This formula can only be applied only for this can be only applied for fully developed laminar flow in a pipe. Laminar flow in a pipe. This formula cannot be applied anywhere else. But this formula, my dear, can be applied for both laminar flow and turbulent flow. It can be applied for laminar flow or turbulent flow to find the major head loss due to friction. Now you must be thinking here, is there any relation between these two we can get from here? So if we are having a laminar flow, and fully developed laminar flow, we have got this head loss. If you equate these two, if we equate equation number 1 and equation number 2, because this can also be applied for laminar flow. So if we equate these two, you will be getting 32 mu VL by rho GD square is equal to FLV square over 2 GD. Right? Here everyone. Or if you just do some cross product here, this will get cancelled out. Sorry, rho will not get cancelled out. This will get cancelled out here. The velocity, one of the velocity will get cancelled out here. The length will get cancelled out here. Ultimately, you will be getting that friction factor will be equal to, friction factor will be equal to 64 into mu divided by rho Vd. As we know that Reynolds number is equal to rho V into d by mu. So we can also say that this friction factor is equal to 64 by Reynolds number. This condition is only applied for friction factor. This is the friction factor. The friction factor can also be written as 64 by Reynolds number only for laminar flow. Only for laminar flow in pipe. You cannot apply this formula for friction factor in any other condition. It can only be applied for laminar flow in a pipe. For laminar flow in a pipe, the friction factor is equal to 64 by Nod's number. And we can say friction coefficient will be equal to 16 by Reynolds number. This is friction coefficient or coefficient of friction or fanning coefficient of friction. Clear everyone? The coefficient of friction will be equal to 16 by Reynolds number and friction factor will be equal to 64 by Reynolds number for laminar flow in a pipe. Is it okay with everyone? Is it clear? So my dear students, I would like to point out a very important thing here, that it is only applied for laminar flow. First of all, this formula can only be applied for laminar flow. If it is a laminar flow in a pipe, then only you can apply this formula for head loss. Okay, we can discuss the, we can definitely, it is correct Manish. For turbulent flow it will be 0.317 divided by Reynolds number power 1 by 4, but that we'll discuss in the turbulent flow topic. Okay, so that is all important for your laminar flow in a pipe. You have to remember some basic formula. Some basic formula you have to remember for laminar flow in a pipe. The formula which is important is, you have to remember the formula for velocity distribution. Local velocity is equal to minus 1 by 4 mu del p over del x into r square 1 minus r square by r square. This is the formula for local velocity. This is the velocity distribution. One more thing, the velocity distribution in the pipe flow is a parabolic velocity distribution. So this is how the velocity distribution will be taking place. The velocity will be maximum at the center and it will be zero at this point. This is a parabolic velocity distribution. I have also told you the shear stress. Shear stress is equal to minus of del p by del x r by 2. This is a local, this is a formula for the shear stress. The maximum shear stress take place at the radius. This is at the wall, we can say it is equal to maximum shear stress in the laminar flow in a pipe. How the shear stress will vary in a pipe? This is how the shear stress varies in the pipe. Okay, it is zero at the center and maximum at the wall. This is how the shear stress will be varying. Okay, this value is the maximum velocity. It is also the maximum velocity. It is minus 1 by 4 mu. For maximum velocity in a laminar flow in a pipe is equal to minus 1 by 4 mu del p over del x of r square. Discharge is equal to minus pi by 128 mu del p by del x d power 4. This is a formula for discharge for laminar flow in a pipe. The average velocity in a laminar flow in a pipe is equal to minus 1 by 8 mu del p by del x of r power square, or we can say average velocity is equal to maximum velocity of half. The pressure drop is equal to 32 mu VL by d square, and the Hagen-Poiseuille equation says that the head loss in a laminar flow in a pipe can also be written as 32 mu VL by rho g d square, and friction factor is also equal to, for laminar flow in a pipe, is equal to 64 by Nod's number. Okay, these are some important point that you have to remember for laminar flow in a pipe. Is it okay with everyone? I have revised all the important formula that you require for solving the problems for laminar flow in a pipe. Okay, clear everyone? Is it clear? What r power 4? Where it will be r power 4, Vikas? Where r power 4? It is, in terms of diameter, it will be minus 1 by 128 mu del p over del x d power 4. In terms of radius, it will be r power 4. Okay, I have written the formula for discharge in terms of diameter. One more important thing, since it is not in the, this is not I have decided for this session, because I feel like just simply telling you the viscous flow through pipe will not be sufficient. So my dear, I would like to point out here a very important point. I can understand that only viscous flow through pipe is important, but if it will be incomplete if I don't tell you the formula for viscous flow through plate. Okay, especially the flow between two parallel fixed plates. So I will be only telling you the some relation which are important for laminar flow between two parallel fixed plates. Let us say we are having two parallel fixed plates. Thickness between the plate is equal to B. B is the thickness between or distance between the two plates. Thickness between plates. We are having two parallel fixed plates. These are the two parallel fixed plates. Okay. So if you have to study the laminar flow between two parallel fixed plates, because I have not decided to see, I have not planned this thing to discuss the viscous flow between two parallel fixed plates, but I feel like I should tell you that because it is important also. Like laminar flow between two in a pipe is important. Laminar flow between two parallel fixed plates is also important. Fixed plate is also important. So I will be only telling you some important formula that you have to remember. Only some important formula. Okay. I cannot teach you everything because I have not planned for it, but I will tell you some important formula which are very important for the laminar flow between two parallel fixed plates. Okay. So my dear students, I would like to point out here for laminar flow between two parallel fixed plates, the velocity distribution you will be getting here is the velocity distribution, the local velocity distribution you will be getting here will be 1 by 2 mu del p by del x 1 by 2 mu. This is a local velocity distribution. I will not tell you how we are getting this because we don't have much time. It is equal to 1 by 2 mu del p by del x b square plus c plus 1 by mu del p by del x of y square. Or right thing, yeah, I should directly tell you the formula. Del p by del x 1 by 2 mu del p by del x of by minus y square. This is a formula for the velocity distribution you will be getting for the flow between two parallel fixed plates. Okay. One more thing, that in the case of laminar flow between two parallel fixed plate, the velocity distribution is parabolic here also. In this case also the velocity distribution will be parabolic. So there will be maximum velocity at the center and there will be zero velocity at the wall between two parallel fixed plates. At the surface of the plate, the velocity will be zero because of no slip condition and it will be maximum at the center. So we'll be having a parabolic velocity distribution here also. It is also parabolic. Okay? Clear everyone? And what will be the maximum velocity in this case? The maximum velocity, you will be getting the maximum velocity when y will become b by 2. Yeah, that will be minus here. Minus sign will be with this. This will be minus sign. Minus sign will be at this point. Here will be having a minus sign. Here. Okay, this is a formula for local velocity. This is a local velocity in the laminar flow between fixed plate. Okay, and this local velocity will become maximum velocity when y will be b by 2 at the center of the pipe, because at center of the pipe when y, the distance from the wall y will become b by 2, at that point u will become u maximum. So when you put y is equal to b by 2, you will be getting u is equal to 1 by 2 mu minus of del p by del x b into b by 2 minus b square by 4. You solve it, you will be getting this value as minus 1 by 8 mu del p by del x of b square. This will be the value of the maximum velocity. Okay, the maximum velocity will be equal to maximum velocity for flow between two parallel fixed plate will be equal to minus 1 by 8 mu del p by del x of b square, where b is the distance between the two parallel fixed plates or thickness between the two plates. Okay. One more thing, the discharge will be equal to minus 1 by 2. The total discharge will be minus 1 by 12 mu del p by del x B cube. This is the value of discharge, total discharge. The average velocity will be equal to minus 1 by 12 mu del P by del X B square. This will be the average velocity. Try to remember that B is the thickness between the distance between the two plates or thickness between the two plates. So this is the local velocity. This is the local velocity, my dear students. This is the local velocity. Okay. This is the maximum velocity. This is the total discharge and this is the average velocity. One more thing, for laminar flow between two parallel fixed plates, the average velocity will be equal to 2 by 3 of maximum velocity. This is a relation between the average and maximum velocity for laminar flow between two parallel fixed plates. Okay. So we can say that the average velocity is equal to 2 by 3 of maximum velocity, and the pressure drop will be equal to 12 into mu into V into L by B square. This will be the value of the pressure drop. Where in this pressure drop between in a flow between two parallel fixed plates, if you have to find the pressure drop between two sections, point 1 and point 2, so pressure drop between these two sections will be equal to 12 into mu VL by B square. B is the distance between the two fixed plates. Clear everyone? Is it clear everyone? All these formulas are clear or not? So this is all important thing which whatever I'm highlighting out here, this is all important thing. These are all very important. Okay, so please be very much careful about this thing, whatever I'm highlighting out here. Clear? These formulas are very important, because sometimes in your exam they will be asking you the formula for, they will be asking you questions on these things from laminar flow between two parallel fixed plates. So these formulas are important. Now let us talk about the shear stress distribution. Shear stress distribution. Shear stress distribution. Shear stress distribution for laminar flow between two parallel fixed plates will be equal to, tau will be equal to minus of del P by del X B by 2 minus Y. This is a formula for the shear stress distribution. Now this shear stress, tau will become tau maximum when Y will become what? Y is the distance from the ball. Y is the distance from the ball. At what, you know that how the shear stress will vary. The shear stress will vary like this. In the laminar flow between two parallel fixed plates, the shear stress will vary like this. Okay. So it will be 0 at the center. That means when Y will be equal to, when Y will be 0, it will be maximum, and when Y will be B by 2, the shear stress will be 0. Okay, this is how the shear stress will vary. So it will be maximum here, it will be 0 at the center. So we will be having a linear distribution of shear stress, and the maximum shear stress will be equal to, in the laminar flow between two parallel fixed plates, that will be minus of del P by del X B by 2. Clear everyone? This is the formula for maximum shear stress. So these are some important points, important formula that you have to remember for laminar flow between two parallel fixed plates. This is also a very important formula. Clear everyone? Yes, is it clear everyone? So at Y is equal to 0, at this particular point, shear stress will be maximum here. At Y is equal to B by 2, that means at this particular point, the shear stress will be 0. Okay, so these are some important formula that I have to point out because these are important from a laminar flow between in a pipe and between two parallel fixed plates. Now let us solve few numericals quickly and then wind up the session. Hurry up. This is the first question that we are going to solve. In a laminar flow through a circular pipe line of 10 cm diameter, the flow velocity at a radial distance of 2.5 cm from the pipe axis is 0.5 meter per second. The maximum velocity is, yes, So we are having a pipe flow. In a pipe flow, we are getting that they have mentioned in the question, the pipe is having 10 centimeter diameter. The diameter of the pipe is 10 centimeter. And at some local radius, at some particular local radius, let us say we are having some local radius at r is equal to 2.5, some local radius, the flow velocity at a radial distance of 2.5 centimeter from pipe axis, that is at r is equal to 2.5 centimeter, the local velocity is equal to 0.5 meter per second. You have to find the maximum velocity. Hurry up, be quick. You know the relation, it is u is equal to u maximum 1 minus r square by r square. This relation I have told you for the laminar flow in the pipe. They have already mentioned it is a laminar flow. So you can apply this equation. The velocity at radial distance of 2.5 centimeter is given. Local velocity is given 0.5. You have to find the maximum velocity. Very simple question. This will be equal to 2.5 is equal to u maximum into 1 minus 2.5 whole square divided by what will be the radius of the pipe? Radius of the pipe will be 5 centimeter. Divide by 5 square. If you solve it, you will be getting the value of maximum velocity. Tell me what is the maximum velocity. Hurry up. Be quick guys, be quick. What will be the maximum velocity? Pratik has got C for this question. Yes, Pratik has got C. Naveen is saying direction. What your direction you are talking about, my dear? Yes, Mohit Kundu has also got C. Yes, the answer will be maximum velocity will be equal to 0.66 meter per second or approximately 0.67. Okay. Next question: maximum velocity in a flow maximum velocity in a flow through a pipe of diameter 400 mm is 12 meter per second. Then velocity at a distance of 16 centimeter from pipe wall. So this question is a little bit important because we have to be very much careful. It is a very important question. It is a very important question. You have to be very much careful about this question. Okay. So what you have to be careful about in this question is, if you see it very carefully, that they have given the maximum velocity. The maximum velocity is equal to 12 meter per second. Here, this is the maximum velocity in this question. The diameter of the pipe is equal to 400. So radius of the pipe will be equal to what? Radius of the pipe will be, the radius will be equal to 200 mm or 0.2 meter. This will be radius. Clear? Manish has got 10.08 as the answer. Now the velocity at a distance of 16 centimeter from pipe wall. From the pipe wall, if they are saying, that means the value of y is given as y is equal to 16 centimeter. This is 20 centimeter. Radius is 20 centimeter. Radius of the pipe is 20 centimeter. The y is the distance from a pipe wall. You have to find the velocity at distance 16 centimeter from pipe wall, because you don't have any relation for y and r, but you know one relation. You know relation between small r, local radius. You know that local radius will be equal to r minus y. That will be equal to 20 minus 16, which will be 4 centimeter. You know the relation between local radius, u is equal to u maximum. See, it is simple thing that you know that whatever will be the velocity at this point from the wall, it will be same velocity from the local radius. Okay. So either you find the velocity from the pipe wall or you find the velocity from the local radius. It will be same. So it will be U is equal to U maximum 1 minus R square by R square. Okay. So you will be getting this as 12 of 1 minus R is 4 centimeter 4 square divided by 20 square. You will solve it, you will be getting the answer. What is the answer you are getting for this question? Manish is getting 4.32, Akshay is getting A. Okay. So some of the students are getting A for this question. So the right answer will be option A, 11.52. If you solve it, you are getting 11.52. 11.52, are you getting 11.52 meter per second for this question? Everyone getting 11.52. Next question. Oil of mass density 850 kg per meter cube and dynamic viscosity 0.025 poise flows through a 5 centimeter diameter pipe of length 400 meter at a rate of 0.2 liter per second. The magnitude of the pressure in Pascal along the pipe is. Yes, be quick guys, be quick. You know that in this question, the density is equal to 850 kg per meter cube. They have already given the density. Okay. The viscosity is equal to poise. It is given in 0.025 poise. You can also write it as 0.0025 Pascal second, because 1 poise is equal to 1 by 10 Pascal second. That is the SI unit of dynamic viscosity, right? Clear? Yes, exactly. All of you are given the right answer for the last question. That was option A. Let's talk about this question. How can you solve this question? You have to find the pressure drop. Pressure drop is equal to, you know the formula, it is 32 mu into V into L by D square. For finding the pressure drop, this is given. That is viscosity is already given in the question. The length of the pipe is also given, that is 400 meter. The rate of discharge is given. So you know that discharge is equal to area into velocity. It is pi by 4 into d square. Diameter is 5 centimeter. That is 0.05 square into velocity. Average velocity. So average velocity. One more important point I have to tell you. In the formula of Reynolds number, you take average velocity. In the formula of this pressure drop, you take average velocity. In the formula of discharge, you take average velocity. So everywhere we have to use average velocity. Okay. So average velocity will be getting from here. Discharge is given to you 0.2 into 10 power minus 3 meter cube per second. This is liter per second. This will be meter cube per second. You will be getting the average velocity from here. What is the average velocity you are getting? Please tell me. Please tell me the average velocity. Yes, hurry up. The average velocity will be equal to 0.1018 meter per second. You will be getting this average velocity. Are you getting this? But one important thing I have to tell you, that see, in the second problem, this is distance. They have simply mentioned that the velocity at a distance of 16 centimeter from pipe wall. From the pipe wall, if they will say, that is simply the value of the y. It is y they are talking about. In the first question, they were talking about the radial distance. They were talking about radial distance of 2 centimeter from pipe axis. They are talking about radial distance. That is local radius they were talking about. They have mentioned it is radial distance. Here they will mention the distance from pipe wall. That is why in this question. Yes, come on, be quick. So average velocity is, you have found, you have to check whether it is a laminar flow or not. You have to find Reynolds number also. You have to find Reynolds number also, and you have to just put all the values. You'll be getting Reynolds number in this equation. That will come out to be how much? 1731.6. Because your Reynolds number is less than 2000, it is a laminar flow. And because it is a laminar flow, you can apply this formula. You can apply this formula because you have confirmed that it is a laminar flow. If you apply this formula, if you put the average velocity, if you put length, viscosity and diameter, everything, you will be getting the pressure drop. The pressure drop will be getting as 1303 1303.04 Pascal. Are you getting this value 1303.04 Pascal, everyone? Yes. Ratna Sanu is getting, Shivani is getting 1303.79, Vikas Yadav 1303.79. Okay, clear everyone? Let us move on to another question. Now this is a question for Laminar flow between parallel plates. In this question they have given that water at 15 degrees Celsius flows between two large parallel plates at a distance of 1.4 mm apart. The pressure drop per unit length is 937.44 Pascal. You have to find the shear stress at y is equal to b by 2. Yeah, I will be teaching the next module tomorrow night at 11 p.m. Correct. So they have given the pressure gradient. The pressure gradient they have given in the question. No, say they have given pressure drop per unit length. They have given Pascal per meter. It has been per meter. The pressure drop per unit length is equal to dp by dx is given in the question 937.44. Sagar Subedi is saying 1.58 for this question. Are you sure, my dear Sagar? Are you sure that this will be the right answer for this question? Yes. You know the formula for pressure drop in the flow between two parallel plates. For parallel plates, the pressure drop is 12 mu into V average into L by B square, where B is the distance between the two parallel plates. The distance between the two parallel fixed plate, that is equal to B, which is given here as 1.4 mm. This is B here. This is already given. So how can you solve this question? It is very simple question, my dear. Hurry up, be quick. So this is a formula for pressure drop, you know that, but in this question, you have to find the value of shear stress. You know that shear stress, I told you, it is equal to minus of del P by del X, B by 2 minus Y. This is the formula for shear stress I have told you. Yes. This is the formula for shear stress that I have told you. Sorry, this will be y is equal to b by 3. I'm sorry. This has to be b by 3. This has to be b by 3. There was a mistake. It has to be b by 3. Okay, it will not be b by 2. It will be b by 3. At b by 2, it will be 0. Exactly. It will be 0 at b by 2. You have to find the shear stress at y is equal to b by 3. Okay. There was a mistake. Yeah, exactly. At b by 2, it will be. At b by 2, it will be 0. But here you have to find it at y is equal to b by 3. There is some correction that I have to do. You have to find y the shear stress at y is equal to b by 3. Yeah, got it. You know the what with the value of shear stress at y is equal to b by 2, it will be 0. But you have to find at y is equal to b by 3. Then how can you find it? Please tell me. If you have to find y at y is equal to b by 3, you have to find the shear stress. Yes. So you have to put the tau will be equal to 937.44 into b by 2. What is b by 2? B by 2 minus b by 3. So that will be simply equal to 937.44 into b by 6. Okay, that will be simply equal to 937.44 into 1.4 into 10 power minus 3 divided by 6. Now I think you will be getting the answer. That will be 0.218. Are you getting the value 0.218 Newton per meter square? Yes, the option B. Clear? Actually, there was a mistake. It has to be b by 3. I'm sorry, I did not notice. So at y is equal to b by 2, it will be 0. But at y is equal to b by 3, you are getting 0.218. The last question of this session. Hurry up. The last question of this session. The magnitude of pressure gradient in kilopascal. The magnitude of pressure gradient in kilopascal per meter for laminar flow of oil between two horizontal parallel plates with maximum velocity of 2 meter per second, which are 80 mm apart. So we are having two parallel plates. Two parallel fixed plates. They are 80 mm apart. The distance between the plate is 80 mm. The maximum velocity is given as 2 meter per second. You have to find the pressure drop per unit length. That means you have to find the dp by dx in this question. Yes, come on guys, be quick. Hurry up, give the answer quickly. So how can you solve this problem? You know that maximum velocity is equal to minus 1 by 8 mu del p by del x of b square. You know this formula? This is a formula for maximum velocity for laminar flow between two parallel fixed plates. So you can use this formula and you can simply tell me the value of pressure gradient del p by del x. Everything is given. The viscosity is given. Distance between the plate is given. Maximum velocity is given. You can tell me the pressure drop. Yes. Hurry up, be quick. Akshay Singh is saying option C, 656.25. Are you getting option C really? Are you getting option C or option B or something else? You have to find the pressure drop in kilopascal. Kilopascal you have to find. Kilopascal. Kilopascal, my dear, kilopascal. Akshay Singh is saying 0.625. Okay. So this is equal to 2 here. It is 1 by 8 mu. Forget minus sign. They are not asking for the sign magnitude. It will be 8 into 2.1 into del p over del x into 80 mm. 80 mm is equal to 0.08 meter. This will be 0.08 square. If you solve it, you will be getting the pressure gradient. Yes, so you will be getting the pressure gradient as how much? The pressure gradient will be getting as 5250 Pascal per meter. In kilopascal, that will be 5.25 kilopascal per meter. So are you getting option D? Are you getting option D or not? Okay, so the right answer will be option D for this question. So that is all in this session. In this session, we have completed the viscous flow through pipe, and also I have told you the formula for viscous flow between two parallel plates. Okay, so with this I would like to conclude the session, and before we complete, I have to tell you that if anybody is interested in preparing for GATE and ESE 2022 now, so you can join our paid course of Vision 2022. It is a paid course for ESE and GATE 2022. You can join it and you can start preparing for GATE and ESE 2022 now onwards. Now this course is ideal for those who are in their BTech second year and third year also. This is a list of the toppers who have got selected by taking our paid courses in engineering services and GATE exam. About Gradeup Super, if anybody has not taken Gradeup Super so far, so you can take Gradeup Super also. Gradeup Super gives you access to all our paid courses. Whether you are preparing for any exam, you can just take Gradeup Super and you can watch any paid course of your choice, or you can also get access to our Gradeup Green Card. With Gradeup Super, you can get access to all our paid courses, whether it is a 3-month course, 12-month course, 18-month or 12 months, which are having different prices. Okay, so we can, with just one Gradeup Super, you can access any paid courses, okay, of your choice. So that is all for today's session. I'm going to see you on tomorrow at 11 p.m. Tomorrow will be the topic of Reynolds and Froude model. So tomorrow we'll be actually studying about the model prototype relation, and because that topic is also important, from lot of question comes from the dimensionless analysis. Okay, so I will be discussing you Reynolds model and fraud model, which is important, and we'll be solving questions tomorrow. Okay, on that topic. So that will be the topic for tomorrow's session, and you will be getting the PDF. The PDF of this session will be getting the Telegram group Gradeup, ESE and GATE /ME preparation. This is the name of our Telegram channel. You can join our Telegram channel. You can join the Telegram channel Gradeup ESE and GATE. This is not dot here. Gradeup ESE and GATE /ME preparation. You can join our Telegram channel. You can. This is the name of our Telegram channel. So you can join our Telegram channel and you can get the PDF of the session. I will upload in the Telegram channel now only. After the session, I will give you the PDF also. So I will upload the PDF in this Telegram channel. I will upload PDF here. Okay. Also, I will see you tomorrow at 11 PM for the topic of Reynolds and fraud model law. And we'll be solving the numericals based on that topic tomorrow. Okay. So thank you so much for participating in this session. I hope you all have learned something from this topic of viscous flow. It is an important topic because many questions come from this topic also. Okay. So thank you so much for joining me and have a very good night. It is already 1 PM. 1 AM. It is 1 PM. It is 1 AM. So good morning we can say, or good night. So I'm going to see you tomorrow night 11 PM. Till then take care, or today at 11 PM. Thank you so much and have a good day. Thank you everyone. And if you have liked the session, then please do not forget to like it also and share it and subscribe the channel. Thank you so much and have a good day. Thank you.